Welcome to this Junior Cycle Higher Level Maths Surds revision video. So we're going to look at surds, which is where we have a square root that can be simplified. There is a very strong link here to indices because square roots and other roots are indices written in a different form. I would suggest that you have gone through your rules of indices and you're familiar with those before starting into this revision video.
So now we're going to move on to surds. So before I talk about surd equations, I just want to go over surds in general. If you just want to look straight away at the surd equations, feel free to skip over. Make sure that you are happy with surds. I suppose surd equations can be asked and other types of questions on surds can be asked. And I suppose some of them mightn't feel relevant here, but I just would like to cover all of the surds together. So surds is just another name for a number which can be written as square roots. Basically what I'm talking about is root 2, root 3 and root 5. So root 4 wouldn't technically be a surd because root 4 simplifies to 2. So any number which is written with a square root, we often call that square root the surd. So we call these surd numbers. So you remember that these numbers are irrational, so hopefully you remember that. So they're infinite non-recurring decimals, so this means they go on forever after the decimal point and they don't repeat themselves. So any decimal version you write down will have rounding. So using this surd form is the most accurate way of writing the number. So for example, if you have your calculator in front of you and you want to do root 2, most new calculators now, if you type in root 2 equals, you'll get back root 2 and you'll have to use the change button or the SD button depending on which calculator you're using to figure out what it is as a decimal. So square root of 2 gives me, and I'll actually just write it in here so you have it. So square root of 2 equals 1.4142135562, and that's where my calculator stops because that's where I've set it to stop. Some people's calculator might do less, some people might do more, but that has been rounded. You might look at it and say, well, really? But actually it has. So if you take that number and you square it again, so type into your calculator 1.4142135562 and square it, you actually get 1.99999. So actually we've made it inaccurate, we've rounded it. So using the surd form is much more accurate than putting it into decimal. I know people don't like the surd form, it's similar to the fractions, but it is the most accurate way. So looking at the properties of surds now, so there are really three that you need to know and you need to be able to work with. And that is, if you have the square root of AB, which means A multiplied by B, you can separate that out. It's like the square root of A multiplied by the square root of B. So if you think of it like this, I have A multiplied by B. That's the same as the square root of A multiplied by the square root of B. So I suppose you could look at this as the multiply can happen underneath the square root or outside the square root. So the second property you need to work with is quite similar. It's about a fraction. So if I have a fraction, and remember with fraction we have division. So really what this is, if I have A divided by B under the square root, it's the same thing as A, the square root of A divided by the square root of B. So remember that fraction means division. So those two are like the opposites of each other. Okay? And then the last property that we have is the square root of A by the square root of A is the square root of A squared, and that equals A. Okay, so basically the square root of A is equal to the square root of A is equal to the square root of A squared, and basically what happens is the A squared and the root, they cancel, so I'm just left with A. Okay, so we can work both ways with that. It's like the square root squared, or you can use it like we had in the first property, that actually you're working backwards, you're putting them back under the same square root. Both will lead us back to A. So it's also important that you're familiar with the perfect squares. So we would have talked about this when we did our factorization, specifically the difference of two squares. It's also quite important to know when you're talking about squares, we will talk about completing the square in different areas, but what we're talking about then with squares are these numbers here. So 1 is a perfect square, 4, 9, 16. So perfect square is a number whose square root is a whole number. So for example, 16 is a perfect square since the square root of 16 is 4. So I would definitely make sure that you know all the way up to 169. So we have 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, and 13 squared. And I do know that you may not have come across 13, but they do love to throw this in, especially with the difference of two squares. 169 is 13 squared. Okay, you can always check on your calculator if it is a perfect square, if it's a much bigger number, or if it's one of those numbers and you just don't recognize it. You can use your square root button. Okay, so for example, if I gave you the number 196 and I said, is that a perfect square? Well, what you would do is put into your calculator square root of 196. So if you have your calculator in front of you, try it now, and you should get 14. So you'd say, yes, it is a perfect square. If I gave you the square root of if I gave you the number 200 and asked, is that a perfect square? Same method, we do the square root. So if you can do that now, put it into your calculator, and what you'll find is you will be left with a surd in the first instance if you're using a new calculator, and what the new calculator will give you is 10 root 2, and if you convert it, it gives you 14.14 on. And basically what that means is it is not a perfect square. So that one is not a perfect square, that one is a perfect square. So just get used to using your square root buttons to help you out in case you don't recognize a number. So let's look at using these properties of surds. Okay, so simplify each of the following. So the method that we use to simplify surds is we're going to try and see, is there a perfect square that will divide into the number? So think of your perfect squares. Okay, we have 1, 4, 9, 16, 25, and so on. Looking at that first one, hopefully everyone will see that 99 can be written as 9 times 11. Okay, and using the first property of surds, we can write that as the square root of 9, square root of 11, and we can simplify the square root of 9 to 3 root 11, and that's your answer. So always the same method. Is there a perfect square that we can divide in? So let's work for the moment just with this bit here. Let's not forget it. I'm going to highlight it because often we can forget it. So I don't want to forget it, and actually it might be easier for us to keep it as we work through our surds so we don't forget it. So square root of 112. So what is the biggest perfect square that can go into it? So we could say 4 goes into it. Does anything else go into it? Well, 16 goes into it, and you can check that. So basically I can separate this into 16 times 7. So what you could do is you'd say, well, the first perfect square is 1. That's not going to be of any help. The next one is 4. So 112 divided by 4. But that gives me 28. And when you see the number 28, hopefully you know that 4 also divides into that. So you'd say, well, actually 4 isn't the biggest perfect square that goes into it. So we're going to get a half of the square root of 16 by the square root of 7. Which gives me a half of 4 root 7, and a half of 4 is going to give me 2 root 7, and that's my answer. Okay, so now we have 2 1/4 under our square root. So in maths, we very rarely use these type of mixed fraction where there's a whole number and a fraction. More likely we are going to use either an improper fraction, okay, or a decimal, okay. So depending on the question, we're going to use an improper fraction or a top-heavy fraction. So hopefully you remember how to do these. The method is 4 by 2 is 8 plus 1, so it gives me 9 over 4. So this is a real flashback to primary school. Hopefully you remember that. Okay. So if you remember our second property of surds, we could rewrite this as root 9 all over root 4, which gives me the square root of 9 is 3 and the square root of 4 is 2. Okay, so these aren't overly complicated, but they do require some practice, like everything, because it's very easy to look and say, oh yeah, that's simple. But sitting in an exam, if you haven't seen them in a while, you might panic and say, I can't remember how to do this. So we're always just trying to find the biggest perfect square that we can divide in. So let's look at example 6. So here we're going to just put a few different simplifications, or a few different of the simplifying together, and then we're going to add and subtract. So express the following as a surd in its simplest form. So this should be one surd. So there's very little I can do with it at the moment. So what I want to find is I want to find what perfect square will divide into 180. Okay, so I could divide 180 by 9 and I get 20. And 20 is divisible by 4, so it's not the biggest. So you can go up, and hopefully what you'll find through a little bit of trial and error if you need to is that this is 36 by 5. Okay, 20 hopefully you can see very quickly is 4 by 5 minus, and this is 25 by 5. So what I'd like to point out at this point is we have a perfect square of 36 and a 5, the perfect square of 4 and a 5, and the perfect square of 25 and a 5. So if you were able to find or able to simplify one of them, and I suppose the one that I would lean towards is the root 20 because it's the simplest, it's the square root of 4 by 5. So the 4 is the perfect square. So if we were to simplify this, it'd be the square root of 4 square root of 5, which will give you 2 root 5. Well, in order to add and subtract, all of those terms would need to have a root 5. So once you have this root 5, you could then really simply divide 5 into 180 and you'd get your 36, and 5 into 125 to get your 25. Okay, so you can do it either way. If you're happy to work with trial and error, or you can be clever about it, work out the simplest and say, well, if I'm going to have to add them, because they did ask for a surd, so they will add and subtract together, they're all going to have to have that square root of 5. So let's tidy up here. So what we have now is square root of 36 by square root of 5, and the square root of 36 is 6 root 5 plus, we still have our 2 root 5, and let's clean up the last term here. It's going to be the square root of 25 by the square root of 5, which is minus 5 root 5. So what I have here is 6 square roots of 5 plus 2 square roots of 5 minus 5 root 5. So I suppose if you think about this as a thing, so I have 6 of something, I add 2 of that something, and then I take 5 away. Okay, so even if we want to say apples, so I have 6 apples, I add 2 apples, so I have 8 apples, and I minus 5 apples, so I have 3 apples. Okay, and I think everyone will be well able to do that. But the square roots are worked in the exact same way. I have 6 of the square roots of 5. Then I add 2, so now I have 8 square roots of 5. And now I'm subtracting 5. So what I'm left with is 3 root 5. So they're added like they are things. Okay, so I have 6 of this thing, I'm adding 2 more, and then I take 5 away. So I'm left with 3 of those things. And I know it's kind of a hard concept to get your head around, but like I said, practice with the surds is really the only thing that will improve with this. It will help you improve your work. So now let's take a look at an example of multiplying out surds. So in this case, we have one bracket. So it works very similarly to algebra. We multiply root 5 by the first piece and root 5 by the second piece. And don't forget your sign. So root 5 by 1 is root 5 minus root 5 times root 5. So here Root 5 by root 5 is root 5 squared, which gives us 5. And our final answer here is root 5 minus 5. If you were given a question like this, you can use your calculator to maybe help you between the steps. So if you wanted to kind of work with this to help you get to 5, but do not enter it directly, because what we need to be able to do is to work with examples like this even when they're not numbers. So it is important that you're able to show your work and you don't just use your calculator to get a final answer. You can of course use your calculator to check your answer, and I highly encourage this. So let's take example 4, multiplying out surds. And in this example, we have 2 brackets. Just like algebra, when we're working with 2 brackets, our working method is to split that first bracket. So we get 3 times the second bracket, which is 5 plus 2 root 7. Then minus root 7 times 5 plus 2 root 7. And let's multiply that out. We get 3 by 5, 3 plus 2 root 7, minus root 7, watch your signs, and minus root 7 times 2 root 7. So 3 times 5 is 15, 3 times 2 root 7. So multiply the rational parts by each other. So the 3 by 2 gives me 6 root 7. Minus root 7 by 5 gives me minus 5 root 7. And here we get minus 2 root 7 times root 7, or root 7 squared. So cleaning this up, we can add these two together. So 6 root 7 minus 5 root 7 is plus root 7. And root 7 by root 7, we said was root 7 squared, which is 7. So 2 times 7, 15 plus root 7, minus 14, which gives us 1 plus root 7. So sometimes students really struggle with working with surds in this way. So one suggestion I have is to treat this surd like you would treat an x. Okay, so if you can imagine everything I've highlighted there as an x, it might make life a bit easier. So 3 multiplied by 2x would be 6x. So 3 times 2 root 7 is 6 root 7. Similarly, when we're adding 6 root 7 minus 5 root 7, think of what you'd do if there was an x. What is 6x minus 5x? So that would leave us with just 1x or x. So similarly, 6 root 7 minus 5 root 7 would give me root 7. Root 7 multiplied by root 7 would give me root 7 squared, the same way that x times x would give us x squared. So sometimes it is a good idea to think of the surds like we would think of a variable in algebra.
Now let's talk about rationalizing the denominator. Remembering that when we have a surd, it is an irrational number. When we talk about rationalizing the denominator, we're trying to get rid of that square root. We're trying to make the denominator a rational number. Now, just an interesting little thing to try is put this little fraction into your calculator. So 1 over root 2 and press equals. Now, if you are using a calculator that doesn't support fractions and roots, you may get a different answer. But if you're using our standard Casio or Sharp calculator, you should get root 2 over 2, like this. And it may look very different, but actually that is the same fraction. They're equivalent. So they don't look the same, but they have the same value. And what the calculator has actually done, it has rationalized the denominator. So instead of writing the denominator as a square root, it is now written it as a rational number, which is 2. So how this is actually done is the top and the bottom is multiplied by the irrational piece of the denominator. So in this case, the whole denominator is irrational. So we multiply above and below the line by root 2. So if we multiply above and below the line by the same thing, so root 2 over root 2, what we're effectively doing is multiplying it by 1. So we're not changing the value of the fraction. So remember, to multiply fractions, we multiply across the top. So 1 by root 2 gives me root 2, and across the bottom, root 2 by root 2. When we square a square root, we're left with simply 2. Now, you might look at that and go, can I simplify it? Well, if you simplify it, you get back to where we started, 1 over root 2. But that's what the calculator is doing, and that's what we need to be able to do as well. So let's look at an example where we are dividing surds. So division is inbuilt in these fractions. So when I talk about dividing, it's because we're doing 2 divided by root 3. So we're going to simplify these, and by simplify, what they're really asking us is to rationalize the denominator. So our first one is 2 over root 3. So in order to rationalize this, we're going to multiply above and below by root 3. When I do that, we get 2 root 3 all over root 3 by root 3 is simply 3, because it's root 3 squared, and the square root cancel. And that's our answer. So all that we need to do in this idea of simplifying is rationalize the denominator, i.e. make that denominator a rational number, a number without the square root. Now, part 2, you could multiply by 2 root 7, but the 2 is not irrational, so it is sufficient to simply multiply by the root 7. Okay, that is because 2 root 7 is all one term. So you can simply multiply by root 7. Now, if you multiply by 2 root 7 above and below the line, you'll just need to simplify using factorization on the last step. And I'll show you what that looks like. But let's do it this way first. Across the top, we get root 7. Now, this one's a little bit trickier because you get 2, that's not changed. Root 7 by root 7 gives me 7, so you get root 7 over 14, and that's our final answer. Now, if you forgot that, or if you think you'd struggle to remember it, and say, well, actually, I will probably multiply by 2 root 7 over 2 root 7. Well, you're still going to get an equivalent fraction that's rationalized, but it may not be in its simplest form. So what we end up with is 2 root 7 over 2 by 2 is 4, and root 7 by root 7 is 7. So we get 2 root 7 over 28. Now, it's not the same answer because it can be simplified. So 2 goes into 2 once, and 2 goes into 28 14 times, which leaves us with the same answer over root 7 over 14. So you just need that extra step to simplify if you don't just multiply by the irrational piece. So then let's look at part 3. So 6 divided by root 2. I'm going to multiply above and below by root 2. When we do that, we should get 6 root 2 over root 2 by root 2, which is 2. Now, in this case, this is not my final answer because I can simplify. Notice that we only ever focus on the rational pieces for simplifying. We never focus on what's underneath the square root. So 2 goes into 2 once, and 2 goes into 6 3 times. So we're left with a much nicer 3 root 2. So now that we've got the basics of rationalizing, what would happen if instead of having a single term under the line, we have 2 terms? So remember, terms are separated by plus and minus. So in the previous example where we had 2 root 7, that's still just one term because they're multiplied together. While here we have root 6 plus 1. So this case, what do we do? So generally what students think we should do is say, well, look, why don't we just multiply it by the whole denominator? So if you tried, and I suppose a step I'm not going to show here, but what if you just multiply by root 6? But if we multiply the denominator by root 6, The root 6 by root 6 would help, but 1 times root 6 would still be root 6. So what we're effectively doing here is we're squaring the denominator. Now, we're not going to call it that because we're not going to square the top and square the bottom because that changes the fraction. Instead, we're going to multiply the denominator by itself and the top by the same. Now, when we do that little workout, root 6 plus 1 by root 6 plus 1, so I squaring it, I've done the workings here, and actually what happens is we're left with quite a nasty looking denominator that definitely is not a rational number. So we can't multiply above and below by root 6. We can't multiply by itself. So instead, and this is something you need to know, it's like a little trick. It's called the conjugate. So we're going to use the conjugate of the denominator. So it's where you do something very similar to what we just did. So root 6 plus 1, but instead of the plus 1, we're going to change that middle sign. So the conjugate of a binomial, so binomial 2 terms, so root 6 plus 1 is a binomial. So instead of root 6 plus 1, we're going to multiply by root 6 minus 1. Now, let's look what happens when we multiply out that bottom line and that sign has changed. For anyone who has been paying very close attention to your factorization, you might cop at this point, we have the answer of a difference of 2 squares. Okay, so if you've caught that, well done. So root 6 plus 1 times root 6 minus 1. But I'm going to do it out in full. Split your first bracket. And then what happens is you get a minus root 6 and a plus root 6. And they cancel. So by changing that sign, you're going to eliminate that root that was in the previous answer. So when we do that, we end up with 2 root 6 minus 2 all over 5. And now we have rationalized that denominator. That denominator, that 5, is a rational number. So the reason I use the word conjugate, and actually it's something that's not really used in this section, is because as we move into the Leaving Cert course, you'll meet this in another form. Well, it looks like a slightly different form, but it is essentially the same thing, and it is called a conjugate. So it's a great thing to know now. Also, it's great to be able to put a word on it instead of talking about take it and change the sign. So the conjugate is where you take that binomial and you change the middle sign. It's important to note that it's not both signs because that won't help. It's just the middle sign. To be honest, it doesn't matter if you wrote that as 1 plus root 6 and then change the root 6, it doesn't matter as long as it's the middle sign in how you've written it. So let's look at an example where we want to rationalize this denominator. So we have 7 over 3 minus root 2. So in order to rationalize, we're going to multiply by the conjugate of the denominator. So that is the denominator, but we change the sign. Remember, we're changing that sign to try and get rid of the irrational part, that square root. I am not a fan of working with fractions. I find them a bit messy, so I like to split it out. BL for bottom line. So that's going to be 3 minus root 2 times 3 plus root 2. I'm going to split my bracket. So 3 times 3 plus root 2 minus root 2 times 3 plus root 2. 3 by 3 is 9 plus 3 by root 2 is 3 root 2 minus root 2 by 3 is minus 3 root 2. Oh, root 2. And minus root 2 by plus root 2 is minus, and then it's 2. Root 2 by root 2 is 2. So now what we have and what we expect are those irrational or surds in the middle cancel out, and I have 9 minus 2, which is 7. So now, if you want, you can work the top line here, and that is 7 times 3 plus root 2. 7 times 3 is 21, and 7 times root 2 is 7 root 2. So bringing it back, we get 21 plus 7 root 2 all over 7. Now, you've got most of your marks, but we're not fully there yet because if you've noticed, 21 and 7 are both multiples of the denominator. So we're going to simplify this. We're going to simplify this like we simplify any algebra fraction, and that is by factorizing. So in the top line, we're going to do highest common factor, which is 7, and we're left with 3 plus 1 root 2, or just root 2. So think of that like an x. If it was 7x, it could just be 1x left, or x. And that's all over 7. And now that we have it factorized, now we can cancel. Remember, cancelling is really division, and division can only happen when we have things broken into factors. So we're left with our final answer of 3 plus root 2.